Hello and welcome to this lecture. So, we've been looking at vector space Fn, F could be R or C, and then we looked at span and subspaces. In particular, the subspaces play a very crucial role. Fn itself is an entire vector space, and inside that there are smaller subspaces that we are interested in. And I gave you the example of how when you want to solve a linear system of equations, you are actually trying to find if a given vector belongs to a subspace or not, right? Belongs to a span of certain vectors, and span of a vector is a subspace. So, the subspace membership or span membership is a very important problem. So, understanding subspaces, understanding spans, what do you do with them, how do you simplify that understanding is a central element of linear algebra and understanding vector spaces. So, let us try and get into this span membership problem or a subspace membership problem and see how we can tackle it for easy cases. Once again, our development will be to do the easy cases first and see how a more general case can reduce to the easy case. So, let us get started. So, here is the problem. You have n vectors or v1 to vn in this Fm vector space, and there is also another vector w, and you ask the question, does w belong to this subspace generated by v1 to vn or subspace spanned by v1 to vn, right. So, this kind of a question is very important. This plays a role in solving linear equations, like I mentioned, and many other type of problems around that. Okay. So, this is something important. So, once again we will start with the easiest case, which is n equals 1. You have only one vector, right, you do not have n vectors, and you ask the question, does w belong to span of v1. This one is particularly easy to solve because v1 could be, let us say, a1 to am, right, m coordinates, and then w could be c1 to cm, m coordinates again, and all I am asking is w in the span of v1, and that is the same as saying, is there an alpha, is there a scalar alpha belonging to this f such that w equals alpha times v1. So, that is all that I am asking, right. So, is there one alpha that if you multiply v1 with that alpha, you get w. That is all we are asking. Basically, that this is what the equation that this alpha has to satisfy. So, c1 has to be alpha times a1. The same alpha when multiplied by a2 should give you c2 and all that. So, all these guys should be multiples of this a1 to am with the same alpha. Now, this can be simplified. When does this alpha exist? There are two cases. One can easily see, if ai is 0, then ci has to be 0. Okay. So, this will help you quickly identify whether this is possible or not. In many cases, you may have ai being 0, but then ci may not be 0, the corresponding ci. So, that immediately rules out the membership problem, right. So, this cannot be a multiple of this if you have this condition violated. Of course, if ai is not 0, for all the i's for which ai is not 0, the ci by ai, when you divide, you should get the same constant alpha. Only then such an alpha exists, right. So, it's a very easy condition, just a simple scaling conditions. So, all you have to ask for the subspace membership problem in n equals 1 is just a scaling test. So, are these above conditions satisfied? If yes, then whatever alpha you got here, w equals alpha v1. If not, then w does not belong to the span of v1. So, the n equal to 1 case, really simple. All your testing is for scaling. A lot of people roughly think of this as c1 by a1 equals c2 by a2 equals cm by am. That is okay, except you will have these 0 by 0 type situations. It is a bit ugly to formalize. If you write like this, it is very clear. Okay. So, n equals 1, very easy. All right. So, we are going to push to n equals 2, right. We go step by step, one after the other. Okay. So, n equals 2, what happens? I am going to ask if w belongs to span of v1, v2. What are v1 and v2? I am going to use these coordinates as the expansion. So, v1 is a11 to a1m, v2 is a21 to a2m. Okay. So, this is my coordinates, and then I have my w, which is c1 to cm. Okay. What am I asking when I ask this question? If w belongs to the span of v1, v2, I have a subspace which is spanned by just two vectors here. I am asking if w can be written as a linear combination of v1 and v2. Is w equal to alpha v1 plus beta v2? Is there any alpha beta for which this is true? Okay. So, it is a slightly more complicated problem. It is not just the scaling of one vector, you are adding two of them, a little bit more involved. Can we solve this problem? Once again, we will take an easy case. Like I said, our approach is always the same. In fact, most of mathematics, almost all of mathematics, this is the approach. Okay. So, you solve an easy case and then think about what cases can reduce to that, etc. Okay. So, here is the easy case. This has been carefully constructed easy case. I will take a special structure for v1 and v2. So, this is the structure. v1 is going to start with a 1, and then the rest I do not care. It can be any, whatever value you want to put there, it can be there. Similarly, v2, now interestingly, the place where V1 is 1, I want V2 to be 0, like, so this 1 0 type thing behavior has to happen, and then I guess the second position is going to be 1 followed by whatever number you want to have. So V1 and V2 have to have this special structure. So this is my easy case. In this case, I'm going to claim that this subspace membership problem is very, very easy to solve. So you'll see why that is true, because if you do alpha V1 plus beta V2, you're getting alpha as the first coordinate, and then alpha A12 plus beta as the second coordinate, and then you have a bunch of these kind of combinations, alpha A13 plus beta A23, so on till alpha A1M plus beta A2M, right? So it's easy to see. I want this to be equal to this W, right? C1, C2, C3 all the way till Cm. Okay. Now I can solve for alpha beta very, very easily, right? So just by inspection, you see alpha has to be C1, and then alpha A12 plus beta has to be C2, which means beta is C2 minus C1 A12, right? Immediately you can solve for an alpha beta. Now these two are not enough. I've equated these two guys. What about all the remaining? They all have to be equal, right? So for every other I equal to 3 to m, I need to have C1 times A1I is basically alpha times A13 plus beta times A23 has to be equal to C3, right? So, and that needs to be true for every I from 3 to m, okay. So, I've solved for alpha beta, fine, but then that same alpha beta should give you equality for all the other coordinates as well, because this one vector equation is not just two equations, it is m equations. Every coordinate has to be equal and you have to equate all those. So, all these conditions have to be true, and these, when they are true, they also give you the value of alpha and beta, okay. So, notice how this 1 0 and A1 2 1, this kind of this 1 0 1 type structure was very crucial in this simplification. Otherwise, we wouldn't have had a simplification. We would have had to do two equations, two variables. We know how to solve it, but still, you know, this is a particularly simple and easy case. So, all you have to do is, if I ask the above conditions satisfied, yes, then W is alpha V1 plus beta V2. No, W does not belong to span of V1 V2. Of course, you can extend this a little bit. You can solve for the two equations and then extend throughout. But you know, this is a simplified case. I'll try and show you how to do the general case in the next step. Okay, so this is easy enough. This easy case looks very nice. What do we do for the general case? It turns out you can use elimination to reduce the general case whenever possible to the easy case. Okay, so that's the crucial word, elimination. This elimination is going to play a big role in these set of lectures. You'll see they are very, very important in understanding a subspace and going forward with it. Okay, what is elimination? Here is how we're going to describe elimination. I'll describe it slightly differently from what we saw before. So the first thing I'll do is I'll think of my A11 as a pivot, and I will assume that A11 is not 0. We'll come back and look at what happens when A11 is 0. You can do some exchange and make the pivot non-zero like we did before, but for now let's just assume A11 is not 0, and I'm going to consider a U1, which is I'll divide V1 by A11 so that my first coordinate becomes 1. Okay, so I'm dividing A11, so I get my first coordinate as 1, and the rest of the guys get divided by A11. That's okay, whatever they are, I don't mind too much, but I have my 1. So notice from V1, I've gone on to this U1, and I have my 1 there in the first place, which is the structure I wanted. What will I do next is to get this 0 type structure below this, right? Below 1, the corresponding coordinate of 1, I wanted a 0. For that, we'll use our standard elimination technique. A11 is not 0, so for U2 tilde, I'll make it as V2 minus A21 by A11 times V1. Okay. So if I do that, you'll see immediately that the first coordinate of U2 tilde has become 0, and then you have other coordinates coming here, right? So the second one will be A22 minus A21 by A11, A12, so on. Okay. So this is okay. This we have seen before. This is what you get. So I'm almost there with U1 and U2 tilde, but then except that this guy is not 1, this guy is non-zero, right? So this guy is, not 1. Okay, I don't know about 0, this is not 0. So I'll assume that the second pivot, which I'll call delta for convenience here, to be non-zero. Okay, I'll assume that the second pivot is 0. Once again, we'll come back and look later what happens if this pivot becomes 0. You may have to exchange, etc. All that we'll see later. But for now, we'll assume that this pivot is non-zero, and then divide by that pivot also and get my U2. So U2 is this U2 tilde divided by this ugly looking delta here, and that you can write in terms of V2, V1, no? Right? U2 tilde is after all this V2 minus linear combination of V2, V1. So substitute back in here, you will get this kind of an expression. So U2 is also a linear combination of V2, V1. U1 is a linear combination of scaling of V1. So you have this U1, U2 here. what is interesting is this guy. Okay, we did elimination is very similar to what we did before. The span of V1, V2 is exactly equal to the span of U1, U2. Okay, while V1, V2 had a more general form, U1, U2 has this very nice 1, 0, 1 form in the beginning, but both the spans are the same. This is a very easy proof. It's very similar to what we did before to show that the spans are the same. So once the span is same, to check if W belongs to the span of V1, V2, it's enough for me to check if W belongs to the span of U1, U2, and that I know how to do, right? It's a very easy case. I can easily check if W belongs to the span of U1, U2. This 1 and 0 structure is particularly very easy for me to solve those equations and get the answer, okay? And this U1, U2 are in the form I want, right? 1 and some U12, U1m, I don't know what they are, some complicated form like this, but it's okay, it's easy enough. U2 is again 0, 1 and then some other form. It will be a little bit more of a fancy expression, but I'll just simply call it U23, U2m for convenience. But nicely enough, this has been simplified to the old case, and now I'm solving the easy case problem and I've reduced it, okay? So n equals 2, the general case we see by elimination with non-zero pivots. Assuming non-zero pivots are there, it reduces to the easy case and we are done, okay? So this is the sort of small steps we take, and as we take enough of these small steps, you'll see a complicated fact would have been shown, and we're already proceeding slowly in that direction, okay? So what if pivots are 0? This we have seen before. Supposing A11 is not 0, A11 is 0, I'm sorry, you find some other position where you have a non-zero value. Now, if you have no position where there's non-zero value, then V1 is 0. It's not an interesting situation, right? Why would you worry about 0? It doesn't give you anything for you. So, we have to assume it's non-zero. So, you have some position where it is not 0, and all you can do is exchange those positions 1 and I in V1, V2 and W. Don't forget W here, because all of them are assuming a certain position and ordering of the coordinates. If you exchange position somewhere, you have to exchange everywhere to keep it consistent, right? So, I'm going to exchange 1 and I will do that in V1, V2 and W. All three I will exchange, right? So, this way I can make my first pivot non-zero. What about the second pivot? So, I'll go ahead and find my U1, okay? So, once the first pivot is 0, I can find my U1. I can also find my U2 tilde, right? U2 tilde will be something here. Here's my second pivot, okay? Is that pivot now going to be non-zero, you may ask, right? So, if it is 0, then hopefully there is another position here somewhere where this U tilde to j is not 0, okay? If that ends up being fully 0, then this U2 tilde itself is fully 0, right? Which means V1 and V2 were linearly dependent to begin with. You go back to the original case, okay? So, that's also something easy for us to do. N equals 1 span membership, we can do that. So, if you assume V1, V2 are linearly independent, then there will be something non-zero here and you can always exchange. So, somewhere here it's non-zero. So, you exchange positions 2 and j, and in all three though, okay, be careful, you have to exchange them in V1, V2 and W. You can also keep track of these exchanges, and after you finally solved it, go back and re-exchange again, okay. So, this is one situation. Pivot 0 can be very easily handled using exchanges. What about the coefficients, right? So, see, given V1, V2 and W, I may want to find alpha beta, okay. It may not be just enough for me to say whether W belongs to the span of V1, V2 or not. I may want to find the exact alpha and beta. If that is your problem, then there is one small thing to worry about, okay. So, we have reduced it to easy case. Let's say we found non-zero pivots, we reduced to easy case, you got U1, U2 and you expressed it like this. Now, I know how to solve this problem. Let's say the answer is yes, there is a AB such that W is AU1 plus BU2. I know how to find A and B, right? It's very easy because of the 1, 0, 1 structure of U1 and U2. I know how to find A and B. How do I go from AB to alpha beta? That is the question, right? So, W has been written in terms of AU1 plus BU2. I know W also belongs to the span of V1, V2, but the coefficients of V1, V2 are alpha beta. These are different. How do I go from here to there? These equations give me the answer, right? It is very easy. So, for U1, U2 in this expression, simply substitute U1 and U2 in terms of V1, V2. I already have that here. You put that in, you will get alpha beta, okay. So, now after you get this alpha beta, there is also this exchanges you may have done. So, just be wary of that, and it's not a big deal, but that won't really alter alpha beta and AB and all too much. The exchanges are just position exchanges. You can do that, that's okay, but be wary of this. So, basically this tells you that what you did to go from V1, V2 to U1, U2 is important. So, you have to record that process of elimination, record these coefficients, keep track of them, so that if you want alpha beta finally, you can go back and substitute. If you did not record this and you went just by just doing the elimination to get U1, U2, you can find span membership, you can find whether W belongs to span of V1, V2 or not. But if you have to find the coefficients alpha beta, you have to keep track of how you did the process of elimination. Can be done as long as you know what it is, you can go back and substitute it. Okay. So, we see that subspace membership for the n equals 1 and n equals 2 case, elimination is already playing an important role. We will see as we go along that elimination plays a central role in our understanding of subspaces and solving problems involving subspaces. Okay, here are a bunch of examples. I'll urge you to try them on your own. So, maybe I'll pick up one problem here and maybe I'll show you how something like this works. So, for instance, here there's a W 1, 2, 3, 4, 5, 6 and the question is it in the span of the following vectors? If it is, then express W as a linear combination of the two vectors. So, maybe I'll pick up one problem, maybe the fourth one, it looks slightly interesting. So, it's 1, 2, 3, 1, 2, 3 and 1, 2, 3, 7, 8, 9 are the V1, V2 and W is 1, 2, 3, 4, 5, 6. So, we have to find out if W belongs to the span of these things and if that works. So, let's quickly do this. So, W is 1, 2, 3, 4, 5, 6. So, I like vectors like this in a sequence. You can see why they are nice. I think easy to write down, good pattern, and V2 is 1, 2, 3, I think 7, 8, 9. Okay. Some of you may be able to quickly guess the answer here, but anyway, let's do it systematically. So, we have this form. I'm going to eliminate and get to U1, U2. U1 is the same as V1, right? So, 1, 2, 3, 1, 2, 3, right? A1, 1 is equal to 1, right? So, you don't have to bother. You can just go this, and U2 tilde is going to be V2 minus V1, right? So, let me just record that U1 was equal to V1. Maybe I should do that carefully. I'm sorry. Just making a mess of things here. V1, 1, 2, 3, 1, 2, 3. U2 tilde is V2 minus V1, isn't it? So, now here you get this interesting little thing 0, 0, 0, 6, 6, 6. That's what you get. Okay. Now, I want this guy to be 1. So, I will exchange 2 and 6, right. So, 2 and 4. Okay. Exchange. So, C2, C4. So, this is my notation to record that I am going to exchange second column and fourth column, right. So, remember W was 1, 2, 3, 4, 5, 6. Okay. So, now when I exchange, my W will become, I'll retain the same notation here maybe, or if you want you can put a W tilde. How many tildes will you put? It's a bit complicated, but usually we just we just write down W tilde and sort of recall. That's how it's going to be. So, it's going to be 1, 4, 3, 2, 5, 6, isn't it? The 2 and 4 I'm exchanging. So, my U1 will become, so I'll just write it as W. So, you should remember that after elimination this has become something else, but it's just better to do like that 1, 1, 3, 2, 2, 3. Okay. I'm exchanging column 2 and column 4. I hope that's clear. And then U2 is just, I'm going to then divide by 6, right. So, let me just do it as 0, 1, 0, 0, 1, 1. Okay. So, you divide by 6 also. U2 tilde C2, C4 exchange divided by 6. Okay. So, it's all just random notation just to keep track. You have to track that you exchange C2 and C4, and this division by 6 is not a big deal. It's U1 and U2 are just scales, so you don't have to, but you should remember that it's important, because you'll see that it became V2 minus V1 by 6. So, when you want to deal with that, when you want to find the actual alpha betas, so you'll have to do this. Okay. So, now I have done this thing. Now, here I can solve what I want to solve, right. So, you can solve very quickly. So, if you want to find W as a linear combination of U1, U2, you see that this alpha is going to be 1 and beta is going to be 3, isn't it? So, you can see that. You see that quickly. Alpha equals C1 and beta is alpha plus beta is 4. So, alpha is already 1. So, beta is going to be 3. Okay, you do not have to remember those formulae. I mean, everybody thinks of the formula, but I think you have to see how the formula comes from. It's very simple, isn't it? Alpha u1 plus beta u2, and I have to only look at the first two coefficients. So, you get alpha equals 1, and then alpha plus beta equals 4, which gives you beta equals 3. Okay. So, you see here quickly that this, let me write the W tilde here just for convenience. W tilde is u1 plus 3 u2. Okay. So, now I hope you see how this exchange happens. So, now there is this exchange that you have to do to make sure that you can go back to the whole thing, but again this will still be true, right? There will be no problem here. You will get the same coefficients working there. So, if you want to go back and write the equations, it should work out. But anyway, for the first step is I am able to write this W tilde as a linear combination of u1, u2, and all the other things are also working. So, you can check that out. So check that out very carefully, right? So, I found 1 and 3 just equating the first two terms. What about the remaining term, right? So, you have to check that that works out. So, this is u1 is 0, 1, 0, I am sorry, u1 is not that, u1 is 1, 1, 3, 2, 2, 3 plus 3 times u2, which is 0. So, I have to put a question mark here, make sure that it's true. 0, 3, 0, 0, 3, 3, and does it check out with W tilde? Yes, indeed it does, right? So, 1, 4, 3, 2, 5, 6. Yes, this is true. So, I can put a tick mark here. My W tilde becomes u1 plus 3 u2. So, the answer is S, right? So, it does belong. W belongs to the span of v1, v2. We are able to quickly establish that. But then, if you have to find the alpha beta, you have to pay some attention to how this worked out, right? So, you can retain u1 as it is, and then so u1 is v1, and then u2 becomes v2 minus v1 by 6, isn't it? v2 minus v1 by 6. Of course, we did the interchange, but the interchange is not going to change your coefficients 1 and 3. You can go back and check that. So, you will get that w equals u1 plus 3 u2. Okay, you can check that that's true, right? So, you can go in and check that w will be u1 plus 3 u2, and here you substitute the u1 and u2 that you got. So, w equals u1 is v1 plus 3 into v2 minus v1 by 6. That will simplify to 1 by 2 v1 plus 1 by 2 v2. Okay. So, many of you might have quickly seen this, and you would have realized that v1 plus v2 by 2 is w, and you would have gotten the alpha and beta. Okay. So, keep track of this, how I did every step and how I got to the standard form, and then I went back to the original form. Notice that any column exchange is not going to change my AB result. What I got as AB here, I will get the same AB here, but this division by 6 I have to keep track of here. Okay, and notice my bad notation. I am using the same u1, u2 everywhere. Be careful about those kind of manipulations. Okay, so simple enough, but you have to pay attention to the details here, and you will get to the answer that you want. Okay, so I will urge you to solve all the other problems as well. Simple manipulations. How do you express one vector as a linear combination of two other vectors? Can be very easily solved using very simple elimination. Thank you very much.